There is a frozen wasteland at the edge of our solar system, filled with hundreds of thousands of icy worlds, rocky debris, and the building blocks of comets that have struck planets, including Earth, for billions of years. This is the Kuiper Belt, and right now, the only spacecraft humanity has ever sent through it is still out there, pushing further into the unknown with every second that passes. Like, subscribe, drop a comment telling me where you are watching from and what you are doing. I genuinely love seeing who is out there. Now let us get into it. The Kuiper Belt is one of those subjects that sounds dry in a textbook, but becomes genuinely staggering the moment you start pulling at its threads. Sit with it long enough, and the numbers stop being abstract. They start feeling real, in a way that is almost uncomfortable, the way it feels when you stand on the edge of something very large and very deep, and your body registers a warning your brain has not processed yet. That is the Kuiper Belt. It sits out beyond the orbit of Neptune, stretching from roughly 30 astronomical units to about 50 astronomical units from the Sun, where 1 astronomical unit is the distance between Earth and the Sun, about 93 million miles. So the Kuiper Belt begins where most people's mental image of the solar system ends, and then it keeps going and going from there, spanning a ring of space so enormous that the entire classical picture of our solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, fits almost neatly inside just the gap between us and where the belt begins. And it is not empty out there, not even close. Scientists estimate the Kuiper Belt contains hundreds of thousands of icy bodies larger than 100 kilometers across, which is about 62 miles in diameter. Alongside those are potentially trillions of smaller objects, chunks of ice and rock, and ancient frozen chemistry tumbling through the dark at temperatures ranging between -220 and -230 degrees Celsius. That is colder than anywhere on Earth has ever been, colder than liquid nitrogen, cold enough that gases which exist freely in warmer environments freeze solid and coat the surfaces of these wandering worlds like paint that has hardened and will never peel. Water ice out there is not slippery and soft the way it is in your freezer. It is as hard as granite, rigid and permanent, a structural material rather than a phase of matter on its way to something else. The belt is sometimes compared to the asteroid belt between Mars and Jupiter, and the comparison is useful as a starting point, but it vastly undersells the Kuiper Belt in nearly every dimension. The Kuiper Belt is roughly 20 times as wide as the asteroid belt. Depending on how you measure it, it is between 20 and 200 times as massive. It is not a single thin ring of debris, but more of a broad, flattened disk of material. And within that disk, the dynamics are complex, the residents varied, and the history stretches back to the earliest days of the solar system itself, when the sun was still young and the planets were just beginning to take shape from a vast cloud of dust and gas and frozen chemistry. To understand why any of this matters, why this frozen and distant ring of debris deserves the title of the most dangerous place in our solar system, you need to understand what the Kuiper Belt actually is, where it came from, what lives inside it, and what it has already done to the worlds closest to the Sun. Because it has done things, big things, world-altering things, things that left scars still visible today in the geological record of multiple planets, in the crater fields that cover the Moon, in the extinct species catalogued in Earth's fossil record, in the chemical composition of the oceans you can see from a satellite photograph. The Kuiper Belt is not just out there being scenic and cold. It has been reaching into the inner solar system for 4.5 billion years, and it is going to keep doing it. Let us start at the very beginning. When the solar system formed about 4.6 billion years ago, it grew from a collapsing cloud of gas and dust. As gravity pulled that enormous cloud of material inward, most of it formed the Sun. The leftover debris began orbiting the newborn star in a disk, slowly clumping together through collisions and gravitational attraction, building the planets and their moons and all the smaller bodies we now catalogue and name and argue about. The inner solar system, sitting closer to the Sun's warmth, produced rocky worlds because the lighter, more volatile materials, water, methane, ammonia, were driven outward by the solar heat during the early phase. Farther out, beyond what planetary scientists call the frost line or snow line, those same materials froze solid and became available to build the enormous cores of the gas giants, and, eventually, to form the bodies of the Kuiper Belt. The Kuiper Belt, understood this way, is leftover construction material. It is the stuff that never quite got built into a planet, either because there was not enough mass concentrated in one region for gravity to pull it all together, or because the gravitational influence of Neptune disrupted the process before it could complete. What remained was this enormous population of primordial objects, each one a frozen time capsule from the era of planet formation, preserved in a deep freeze so extreme that even geological processes slow nearly to a halt. The surfaces of Kuiper Belt objects can remain almost unchanged for billions of years, which is precisely what makes them scientifically valuable. They are samples of the original material that built the solar system, sitting in a refrigerator so cold that nothing has degraded them. But here is where the story gets complicated, and dangerous, and fascinating, all at once. The solar system did not simply form and then settle into the peaceful, orderly arrangement we see in diagrams today. For hundreds of millions of years after the planets first took shape, the solar system was a violent, churning catastrophe. The giant planets, Jupiter, Saturn, Uranus, and Neptune, were not always in their current orbits. They migrated, and that migration had consequences for the Kuiper Belt that reverberate across geological time and still echo today, right now, in the comets that occasionally light up the night sky above your house. A theoretical framework called the NICE model, developed by a team of planetary scientists including Alessandro Morbidelli, Harold Levison, Cleomenis Tsiganis, and Rodney Gomes, and named after the city of Nice in France, where much of the collaborative work was carried out, describes what happened in the early solar system in alarming detail. According to this model, early in solar system history, Jupiter and Saturn's gravitational interaction created a resonance between the two giant planets that triggered a cascade of orbital changes throughout the outer solar system. This resonance caused Uranus and Neptune to migrate outward from their original positions. As Neptune swept outward through what was then a far more densely populated proto-Kuiper Belt, it acted like a cosmic plow, scattering objects in every direction. Most of them were flung out into the far reaches of the solar system, or ejected from the solar system entirely, lost to interstellar space. A fraction of them were scattered inward toward the planets. The result was a period of extreme bombardment that lasted from approximately 4.1 to 3.8 billion years ago, a period now called the Late Heavy Bombardment. During this time, the inner planets, including Earth and the Moon, were pelted by enormous numbers of comets and asteroids, originating partly from the outer solar system, including what was then a much more massive Kuiper Belt. The craters that pockmark the surface of the Moon, visible to the naked eye from Earth on a clear night, are largely a monument to this period. Ancient impact basins on Mercury, Mars, and Earth itself tell the same story. The oceans on Earth may even owe part of their existence to the water delivered by these impacts. Water ice carried in from the outer solar system by comets sourced from the Kuiper Belt region. Volatiles that had spent hundreds of millions of years frozen in the outer dark before a gravitational nudge sent them falling inward to melt on the surface of a warming rocky world. The Kuiper Belt we observe today is a shadow of what it once was. Current estimates put its total mass at roughly 1/10 to 1/20 of Earth's mass, a tiny fraction compared to what models suggest it must have contained early in solar system history in order to have grown the substantial objects we find there now. The missing mass was scattered away, flung outward or inward by Neptune's migration during that ancient violent period. What remains is a depleted, ancient reservoir, still dangerous, still active, still sending material toward the inner solar system, but greatly diminished from its primordial state. Something like 99% of what was originally out there is gone, removed by billions of years of gravitational stirring. What is left are the survivors. Now let us talk about the people who figured all of this out, because the history of how humans discovered the Kuiper Belt is every bit as interesting as the belt itself, full of persistence and coincidence and the kind of detective work that takes decades before yielding a result. Pluto was the first clue, though for decades nobody recognized it as such. On the morning of February 18, 1930, a young astronomer named Clyde Tombaugh was working at the Lowell Observatory in Flagstaff, Arizona, comparing photographic plates of the night sky taken several days apart. His method was painstaking and unglamorous. Load a plate into a device called a blink comparator, alternate rapidly between two images taken of the same region of sky on different dates, and watch for anything that had moved relative to the background stars. Stars stay fixed. Planets, asteroids, and other solar system objects shift their position from night to night because they are much closer to us and moving. Tombaugh had been doing this for almost a year, plate by plate, hour by hour, searching systematically for evidence of a ninth planet that the observatory's founder, Percival Lowell, had predicted years earlier based on gravitational irregularities in the orbits of Uranus and Neptune. On that February morning, Tombaugh spotted something. A tiny dot of light had shifted position between images. He called his supervisor over to confirm what he was seeing. The discovery was announced to the world on March 13, 1930, on the 75th anniversary of Lowell's birth and the 149th anniversary of the discovery of Uranus, and the new object was given the name Pluto. The name came partly from the suggestion of an 11-year-old girl in Oxford, England, named Venetia Burney, who thought the name of the Roman god of the underworld was fitting for such a dark, distant world. The first two letters of Pluto, PL, also served as a tribute to Percival Lowell. For the next 62 years, Pluto sat alone at the edge of the known solar system, classified as the ninth planet, an oddity in many respects. It was much smaller than the other outer planets, with an orbital inclination and eccentricity unlike any of the others. Its orbit is tilted 17 degrees relative to the plane of the solar system, and its path is elliptical enough that it sometimes swings closer to the Sun than Neptune. Astronomers suspected something might be out there beyond Pluto, but the technology to find it did not yet exist. In 1943, the Irish-Scottish astronomer Kenneth Edgeworth published a paper suggesting that the region beyond Neptune likely contained a population of small bodies left over from the original solar nebula. He proposed that the outer part of the original disk of solar system material had been too sparse and too cold for these bodies to accumulate into a single planet, and that they therefore remained scattered throughout the outer solar system. In 1951, Dutch-American astronomer Gerard Kuiper published a paper on the formation of the solar system that also discussed the possibility of a remnant disk of icy bodies beyond Neptune. Though Kuiper's paper actually argued these bodies would have been expelled from the region due to gravitational interactions, a prediction that turned out to be wrong. Edgeworth made similar proposals around the same time, which is why some researchers believe the belt should properly be called the Edgeworth-Kuiper Belt. In common usage, however, it is almost always simply called the Kuiper Belt, despite Kuiper himself having expected the region to be essentially empty. The theoretical case for a belt of objects beyond Pluto had been building for decades, but actually confirming it required finding something out there, and finding something out there required a systematic search that previous technology could not support. That changed as telescope instrumentation and photographic techniques improved through the 1980s. David Jewett was an astronomer who had become convinced that the outer solar system must contain a population of small bodies similar to what Edgeworth and Kuiper had described. Working with Jane Liu, a graduate student and then postdoctoral researcher, Jewett began conducting a systematic search using the 2.2-meter telescope at the Mauna Kea Observatory in Hawaii. The search was methodical, unglamorous, and, for years, completely fruitless. They were looking for faint, slow-moving objects in the outer solar system, and the outer solar system is a very large place. For 5 years they found nothing that qualified. On August 30th, 1992, that changed. A faint, slow-moving object appeared in their images that did not behave like a known comet or any previously catalogued solar system body. It was designated 1992 QB1, and it became the first confirmed Kuiper Belt object beyond Pluto. Jewett later described the discovery as the result of sheer persistence. The find opened the floodgates. Within a few years, dozens and then hundreds of KBOs had been found by teams around the world. The professional astronomical community began to understand that Pluto was not a lone oddity at the edge of the solar system, but rather the largest known member of an enormous population of similar objects inhabiting this frozen outer ring. Among the people who began hunting KBOs in earnest in the years that followed was Michael Brown, an astronomer at Caltech, whose subsequent discoveries would eventually force a reckoning with one of astronomy's most deeply held popular beliefs, that the solar system has 9 planets, and one of them is Pluto. Brown and his collaborators, Chad Trujillo and David Rabinowitz, were responsible for discovering several of the largest known KBOs in quick succession during the early 2000s. In 2002, they discovered Kuiper, an object about 1,110 kilometers in diameter, with its own small moon, orbiting the Sun at roughly 43 AU. In 2003, they found Sedna, an object so distant and so strangely positioned that its very existence challenged what scientists thought they understood about the solar system's structure. Sedna orbits the Sun at distances ranging from about 76 AUs at its closest approach to a staggering 937 AUs at its farthest, a journey through the outer darkness that takes approximately 11,400 years to complete one full orbit. When the earliest human civilizations were building the first cities in Mesopotamia, Sedna was somewhere in its orbit that it will not return to for another 11 millennia. In 2004, Brown's team discovered Haumea and Makemake, two more large objects in the outer solar system, and then in 2005 came the discovery that would ultimately change the textbooks. On January 5, 2005, Brown, Trujillo, and Rabinowitz detected a new object in the outer solar system from images taken at the Palomar Observatory in California. It was provisionally designated 2003 UB313 before being officially named Eris, after the Greek goddess of discord and strife, a name chosen partly because of the controversy it would create. Initial measurements suggested Eris might actually be larger than Pluto, and news outlets quickly labeled it the 10th planet. Even Brown in those early days used that terminology. The object seemed to demand it. But the discovery of Eris put the scientific community in an impossible position that could no longer be avoided. If Pluto was a planet, then so was Eris. And if Eris was a planet, what about Makemake, Haumea, Kuiper, and all the other large KBOs that were now turning up? Where exactly did the line get drawn? Astronomers had been quietly debating Pluto's classification for years, ever since the Kuiper Belt's existence became clear, and it became obvious that Pluto was not a lone ninth planet, but rather the largest of many similar bodies. Eris forced the question from the back rooms of professional conferences into the open. On August 24, 2006, at a General Assembly of the International Astronomical Union in Prague, Czech Republic, delegates voted to adopt a new formal definition of the word planet. Under this definition, a planet must orbit the Sun, must have sufficient mass to pull itself into a roughly spherical shape under its own gravity, and must have cleared the neighborhood around its orbit of other debris. That third criterion was the critical one, and Pluto failed it. Surrounded by other KBOs, embedded in a belt of thousands of similar objects, Pluto had not cleared its orbital neighborhood. By the IAU's new definition, it was reclassified as a dwarf planet, joining Eris and Ceres, a large object in the asteroid belt between Mars and Jupiter, in this newly created category. The public reaction was intense, and by the standards of scientific debates, remarkably personal. Millions of people had grown up with Pluto as the ninth planet, had learned it in school, had some degree of sentimental attachment to the small and distant world at the edge of the solar system. The demotion felt to many like a betrayal, a cultural loss, a rewriting of something that had been fixed and certain for 3 generations. Children wrote letters to observatories, petitions circulated. The state of Illinois, where Clyde Tombaugh had been born in 1906 in Streator, passed a resolution in 2009 declaring that Pluto would always be considered a planet within state borders, and that March 13 would be celebrated as Pluto Day. Bumper stickers appeared. The verb to Pluto was coined, meaning to demote or devalue something. Among the most prominent and persistent scientific voices against the reclassification was Alan Stern, the planetary scientist at the Southwest Research Institute in Boulder, Colorado, who served as the principal investigator for NASA's New Horizons mission. Stern argued then, and continues to argue, that the IAU's definition was poorly constructed, that it would technically exclude Earth, Mars, Jupiter, and Neptune themselves from being called planets if those bodies were placed in Pluto's orbital location, and that the vote itself was procedurally flawed since only a fraction of IAU members were present and voting when the definition passed. Stern favors a geophysical definition of planet, one based on whether an object is massive enough to pull itself into a spherical shape, which would make Pluto a planet, and also add several other large KBOs to the planet count. The controversy has never fully resolved. For the purposes of science, the categories are tools, and the question of what to call Pluto is less important than what Pluto actually is, which, as New Horizons revealed, is something extraordinary. New Horizons was launched on January 19, 2006, from Cape Canaveral, Florida, and the timing was remarkable. The spacecraft launched just months before the IAU vote that would reclassify the world it was traveling to visit. Built and managed by the Johns Hopkins University Applied Physics Laboratory, with Alan Stern as principal investigator, New Horizons became at the moment of its launch the fastest spacecraft ever sent from Earth, traveling at approximately 36,000 miles per hour, which is about 58,000 kilometers per hour. Then it kept going and going through the outer solar system, silent and purposeful, crossing the orbits of Saturn, then Uranus, then Neptune. While back on Earth, the world changed around the people waiting for it to arrive. Smartphones went from novelty to necessity. Social media platforms rose and fell. The global financial crisis came and went. And every day, New Horizons covered another roughly 800,000 miles. The tension at the Johns Hopkins Applied Physics Laboratory in the days before the Pluto flyby on July 14, 2015, was almost physically palpable. Mission planners had spent enormous effort determining whether New Horizons could safely navigate through the Pluto system, and the specific worry was the debris environment. Pluto has moons, and those moons could be generating rings or debris clouds through micrometeorite bombardment of their surfaces. If New Horizons flew through a dense ring of such material at 36,000 miles per hour, even particles measuring just a millimeter across could penetrate and destroy the spacecraft. The mission team worked through multiple alternative flight paths, trading science return against hazard risk, and ultimately concluded that the primary planned trajectory was safe. They flew it as originally designed. At 7:49 in the morning Eastern Time on July 14, 2015, New Horizons made its closest approach to Pluto, passing within about 7,800 miles of the surface. The spacecraft was traveling so fast that the entire closest encounter lasted only minutes. Because of the vast distance between Pluto and Earth, radio signals took about 4.5 hours to make the one-way trip, which meant that by the time mission controllers received confirmation that New Horizons had survived its flyby, the spacecraft had already moved far beyond Pluto. The team had to wait those hours knowing the spacecraft had already either survived or not. There was nothing more anyone on Earth could do. The moment the confirmation signal arrived, the control room erupted. What the spacecraft found was not what anyone expected. Or rather, the surprises were not in the absence of features, but in the presence of them, and in what those features implied. Scientists had been fairly confident Pluto would be a geologically dead world. Cold, ancient, heavily cratered, inert, preserved in its original state much like a frozen artifact. Instead, New Horizons revealed a world of surprising variety, complexity, and even geological activity. The most immediately striking feature, visible even in the first rough images transmitted back, was an enormous, heart-shaped pale region stretching across a broad portion of Pluto's surface. Scientists named it Tombor Regio in honor of Clyde Tombaugh, who discovered Pluto 85 years before the flyby. Within Tombor Regio lies a smooth, pale plain of nitrogen ice called Sputnik Planitia, remarkable for its almost complete absence of craters. The lack of craters implies a geologically young surface, and the best current estimates suggest Sputnik Planitia may be as young as a few tens of millions of years, essentially modern in geological terms. Convection cells within the nitrogen ice, driven by heat from Pluto's interior, percolating upward, slowly churn the surface material even today, erasing craters and refreshing the surface continuously. Mountains on Pluto are made of water ice and rise as high as 11,000 feet, comparable to parts of the Rocky Mountains on Earth, standing up through the nitrogen ice plains like islands. The surface shows signs of glaciers, valleys carved by flowing ice, and what may be ancient nitrogen ice rivers that once ran across the landscape. Pluto has a thin but layered nitrogen atmosphere that extends hundreds of miles above the surface in a series of hazes visible against the backlit limb of the planet in New Horizons images. Images that, when they arrived and were processed, stopped people cold. Not because Pluto was the most extreme or the largest or the most dramatic object New Horizons could have visited, but because seeing it as a world, seeing its mountains and its plains and its blue hazes, made it real in a way it had never been before. There are regions of Pluto-colored, deep red-brown by compounds called tholins, complex organic molecules formed when nitrogen and methane in the atmosphere are struck by ultraviolet radiation from the sun and energetic particles from the solar wind and react to form larger, more complex chemical structures. These tholins are of intense interest to astrobiologists because similar chemistry may have occurred in the atmosphere and on the surface of the early Earth before life began, when the Earth's own atmosphere was rich in nitrogen and methane and the sun was irradiating the surface with radiation that would today be blocked by the ozone layer. Pluto's tholins are not life, not even close, but they are the kind of organic chemistry that can be a stepping stone toward it, and their presence on a world in the Kuiper Belt says something interesting about how widespread such chemistry might be in the solar system. The flyby produced more than 50 gigabits of data in total, and downloading it all back to Earth at the slow transmission rates possible at that distance took more than a year. Each batch of new images and measurements generated new surprises, new puzzles, new scientific papers. Pluto had gone from an astronomical footnote, the demoted dwarf planet that half the internet still argued about, to one of the most scientifically interesting objects in the solar system. New Horizons was not done. After Pluto, the spacecraft was redirected toward another target deep in the Kuiper Belt, a small, distant object originally designated 2014 MU-69. The mission team nicknamed it Ultima Thule, a classical and medieval term for a distant, extreme, or mysterious place beyond the boundaries of the known world. The name seemed fitting for something at the edge of explored space. On January 1, 2019, New Horizons made its closest approach to Ultima Thule, and what it found there was something that nobody had fully predicted in its specific form, though the general possibility had been anticipated. The object was a contact binary, two separate lobes, two original bodies that had formed separately in the same region of the primordial solar nebula, had gradually come together over millions of years as their orbits slowly aligned, finally merging at extremely low velocity, perhaps just a few meters per second, barely faster than a person walking. They joined so gently that neither shattered, and the result was a shape something like a snowman, about 22 miles long from end to end. The two lobes were called Ultima and Thule before the object received its official name, Arrokoth, a word from the Powhatan and Algonquian languages meaning sky. Arrokoth sits about 44 astronomical units from the Sun, making the New Horizons encounter the farthest close exploration of any solar system body in history at that time. Its surface is uniformly reddish from tholins and shows relatively few craters, suggesting it has sat largely undisturbed since the earliest days of the solar system. This preserved state makes it extraordinarily valuable as a scientific specimen. By studying how Arrokoth formed and what it is made of, scientists can learn about the very first steps of planet formation, how small grains of dust and ice in the primordial solar nebula began clustering and sticking together into larger and larger bodies. The picture that emerges from Arrokoth is one of gentle accumulation. The two lobes appear to have formed in nearby parts of the same collapsing cloud of material, to have slowly approached each other as their orbits decayed through the drag of surrounding gas and dust, and to have touched and merged quietly, like two soap bubbles coming together instead of two billiard balls colliding. This model of planet formation, which scientists call pebble accretion in some forms and streaming instability in others, suggests that the outer solar system's building blocks formed through patient accumulation rather than violent collision, at least in their earliest stages, before they grew large enough for gravity to dominate. Arrokoth is, in this sense, a preserved ancestor of larger Kuiper Belt objects, a before photograph from a time before gravity could do more of the work. Now let us talk about what the Kuiper Belt has done to the rest of the solar system and what it can still do. Short-period comets are the most direct and dramatic expression of the Kuiper Belt's influence on the inner solar system. These are comets with orbital periods of less than 200 years, comets that return regularly enough that human observers have been able to see, record, and track them across multiple passes. They originate in the Kuiper Belt when gravitational perturbations, most often from Neptune, knock objects out of stable orbits, and send them drifting inward, pulled by the sun's gravity, accelerating as they go. As they approach the inner solar system, the sun's growing heat reaches the surface of the comet nucleus and begins vaporizing ices, blowing off a glowing coma of gas and dust around the nucleus and extending it into the long, bright tail that has frightened and fascinated humans since before recorded history. The tail of a comet always points away from the sun, not behind the comet. This is because the solar wind, a stream of charged particles flowing outward from the sun at all times, pushes the material of the tail radially outward from the sun, regardless of which direction the comet is traveling. A comet approaching the sun has a tail pointing away from the sun and ahead of it. A comet receding from the sun has a tail also pointing away from the sun, meaning the tail now follows behind. This counterintuitive behavior puzzled ancient observers who tried to understand comets in terms of earthly objects they recognized, and it was not fully explained until the era of modern astronomy. But beauty and danger are not mutually exclusive properties, and comets have a track record of violence in this solar system that places them among the most destructive forces we know of. The most dramatic modern demonstration of what a Kuiper Belt-derived object can do to a planet came in the summer of 1994, when comet Shoemaker-Levy 9 crashed into Jupiter. The comet had been captured by Jupiter's enormous gravity at some earlier point and pulled into orbit around the giant planet. On one of its close passes around Jupiter, tidal forces, the difference in gravitational pull across the comet's diameter, tore the nucleus apart into a string of at least 21 fragments, ranging from a few hundred meters to perhaps 2 kilometers in diameter. These fragments spread out along the orbital path like a string of pearls. Between July 16 and July 22, 1994, these fragments struck Jupiter in rapid succession, each one plunging into the atmosphere at high velocity and detonating with energy vastly beyond anything in the human frame of reference. The largest single impact, from the fragment known as Fragment G, released energy estimated at roughly 6 million megatons of TNT. To put that in perspective, the most powerful nuclear weapon ever tested, the Soviet Tsar bomber, released energy equivalent to about 50 megatons of TNT. Fragment G released about 120,000 times that energy in a single impact. The total energy released across all 21 impacts over those 6 days exceeded by far the total estimated nuclear arsenal of every nation on Earth at the time. The impacts left dark, circular marks in Jupiter's cloud bands that were visible through small amateur telescopes for months afterward. Some of these marks were larger than the diameter of Earth itself. Astronomers around the world and the Hubble Space Telescope and several planetary spacecraft watched this unfold in something approaching real time. For the first time in recorded human history, humanity witnessed a major solar system collision as it happened, live, with instruments sophisticated enough to measure what was occurring. The event was breathtaking and sobering in equal measure. It was a visceral reminder, impossible to dismiss, that the planets are not floating in a safe and static void. The solar system is an active environment, and impacts happen, and the Kuiper Belt is one of the primary sources from which the impacting objects come. The connection between the Kuiper Belt and impacts on Earth runs deep into the geological and biological record of our planet, through hundreds of millions of years of history that are only now beginning to be fully mapped. About 66 million years ago, a massive impact event occurred in what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater, an impact structure roughly 93 miles across, buried beneath the Gulf of Mexico and the coastal sediments of Mexico. This impact triggered enormous fires, injected enough dust and debris into the upper atmosphere to block sunlight globally for months to years, caused temperatures to plunge, disrupted plant growth, and ultimately triggered the mass extinction event that wiped out roughly 75% of all species then alive on Earth, including every species of non-avian dinosaur. The primary impactor is generally believed to have been an asteroid originating from the inner solar system, but some researchers have proposed that cometary material from the outer solar system, including potentially from the Kuiper Belt, may have been involved in the extinction event, or that a broader cometary shower may have accompanied the impact. Whether or not a Kuiper Belt object was directly responsible for the Chicxulub impactor, the broader principle stands without qualification. The Kuiper Belt is an ongoing source of objects that can reach Earth, and the history of Earth is written partly in the impacts they have caused. Every large crater on the surface of our planet, every mass extinction event linked to an impact, every moment in the geological record where life on Earth was nearly erased and had to begin the long, slow process of rebuilding. These are the fingerprints of a universe that does not distinguish between inhabited worlds and empty ones, that does not set aside safe zones for biology. And this is not just ancient history. Comets that originated in the outer solar system continue to arrive in the inner solar system regularly. Some of the most memorable astronomical events of the past few decades have been cometary. Comet Hale-Bopp blazed spectacularly across the night sky in 1997, visible to the naked eye for a record-breaking 18 months, making it one of the most widely observed comets in history. It originated from the outer solar system, with a previous close approach to the Sun estimated to have occurred roughly 4,200 years ago. Comet 67P/Churyumov-Gerasimenko orbited and studied in extraordinary close detail by the European Space Agency's Rosetta mission between 2014 and 2016, is a Jupiter family comet believed to have originated in the Kuiper Belt before being gravitationally redirected inward by the giant planets over millions of years. The Rosetta mission and its Philae lander, which became the first human-made object to land on a comet nucleus in November 2014, revealed 67P as an object of startling complexity, covered in organic molecules, water ice, a landscape of cliffs and boulders, and gas-venting jets, active and strange and unlike anything anticipated from a distance. Between the Kuiper Belt and the inner solar system sits a transitional population of objects known as centaurs. These are small bodies with orbits between Jupiter and Neptune, objects that were once Kuiper Belt residents and were gravitationally perturbed inward by Neptune or by encounters with other large KBOs until they found themselves crossing the orbits of the giant planets. Centaurs are inherently unstable. Their orbits are subject to strong gravitational perturbations from the giant planets, and over time, millions of years on average, they will either be ejected from the solar system entirely, collide with a planet or the Sun, or be gradually scattered into short-period comet orbits that carry them into the inner solar system, where the Sun's warmth activates their ices and they begin to display the characteristics of classical comets. Chiron, discovered in 1977, was the first recognized centaur, and it was classified initially as an asteroid before astronomers noticed it had a faint coma developing around it, indicating it was also behaving like a comet. Today, dozens of centaurs are known, and the population is estimated to be in the thousands. Each one is a Kuiper Belt object in transit, spending a few million years in its intermediate orbit before its fate, ejection, collision, or cometary activation, is settled by the relentless mechanics of planetary gravity. Now let us spend some time with the specific inhabitants of the Kuiper Belt, because these are not just data points and catalogue numbers. They are worlds, each one strange and specific, each one telling its own story about the history and structure of the outer solar system. Pluto remains the most famous resident of the belt, and what New Horizons revealed about it transformed the conversation from a debate about classification to something more interesting, a discussion of what kind of world Pluto actually is. Pluto has a diameter of about 2,377 kilometers and orbits the Sun at an average distance of roughly 39.5 astronomical units. A Plutonian year lasts about 248 Earth years. When Pluto was discovered in 1930, it had already completed about a third of its orbital journey, since being classified as a planet the last time it passed that region of its orbit, roughly in the 1680s. Even after more than 9 decades since its discovery, Pluto has completed less than half an orbit since being found. Pluto has 5 known moons: Charon, Nix, Hydra, Kerberos, and Styx. Charon, the largest, is enormous relative to its host body, with a diameter of about 1,212 kilometers, roughly half of Pluto's diameter, and massive enough that the center of mass of the Pluto-Charon system, the point around which both bodies actually orbit, lies in the space between them rather than inside Pluto. This makes the Pluto-Charon system, in a meaningful physical sense, a double dwarf planet system rather than a planet with a moon. The two worlds are tidally locked to each other, meaning each always shows the same face to the other, and from Pluto's surface, Charon would sit motionless, in the same position in the sky, neither rising nor setting. Charon's surface is darker and more reddish toward its north pole, a feature known as Mordor macula, and this coloring is believed to result from organic molecules that escape from Pluto's thin nitrogen atmosphere into space, travel to Charon, and freeze onto Charon's surface in the polar region where temperatures are lowest. Over millions of years, these frozen organic compounds are transformed by radiation into the complex reddish tholins that color so many objects in the outer solar system. The two worlds exchange material across the space between them, one feeding the other with the slow drift of escaped atmosphere. Pluto has a thin but real nitrogen atmosphere that expands when Pluto is at perihelion, closest to the Sun, and contracts and partially freezes onto the surface when Pluto moves farther away toward aphelion. In the years after New Horizons, as Pluto moved farther from the Sun in its elliptical orbit, ground-based observations began tracking the expected collapse of the atmosphere, a slow seasonal shift occurring over decades. Eris, discovered by Brown, Trujillo, and Rabinowitz in 2005, is the body that triggered the planetary definition crisis and has a name, chosen after the Greek goddess of discord, that proved almost prophetically appropriate. With a diameter of about 2,326 kilometers, Eris is marginally smaller than Pluto in physical size, a reversal from early measurements that initially suggested it was larger. Despite being slightly smaller, Eris is about 27% more massive than Pluto, meaning it is denser, with more rock relative to ice in its composition. Its surface is bright, likely covered with frozen nitrogen and methane that are highly reflective. Eris spends most of its orbit far beyond the classical Kuiper Belt, in a region called the scattered disk, reaching distances of about 98 AUs at its farthest point. One moon, Dysnomia, orbits Eris. Makemake, discovered by Brown's team and officially announced in 2005, orbits roughly in the classical Kuiper Belt, completing one orbit every 305 Earth years. With a diameter of around 1,430 kilometers, it is the third largest known dwarf planet in the Kuiper Belt after Pluto and Eris. Makemake's surface is covered with frozen methane, ethane, and nitrogen, giving it a reddish-brown color similar to many other outer solar system bodies. A small dark moon was discovered orbiting Makemake in 2016 by the Hubble Space Telescope, designated S20115, 1036-472-1000, and nicknamed MK2 informally. The moon's dark color, contrasting sharply with Makemake's bright surface, is puzzling and not fully explained. Haumea is perhaps the most immediately striking of the Kuiper Belt's dwarf planets simply because of its shape. Discovered by Brown's team in 2004 and formally announced in 2005, Haumea spins so fast that it has been stretched into an elongated ellipsoid, flattened at the poles and extended at the equator by centrifugal force. It completes one full rotation in about 3.9 hours, making it one of the fastest rotating large bodies in the solar system. From end to end along its longest axis, Haumea measures about 2,100 kilometers, but its shortest axis is only about 996 kilometers. It is shaped something like a rugby ball or a compressed football. Two moons orbit Haumea, Hi'iaka, the larger outer moon, and Namaka, the smaller inner moon. In 2017, astronomers discovered that Haumea also has a ring, the first ring system ever found around a Kuiper Belt object. What makes this ring scientifically interesting, beyond the novelty of its existence, is that it sits in an orbital resonance with Haumea's rapid rotation, and its location challenges some existing models of how rings form around small bodies. Haumea is also the center of what is called a collisional family, a group of Kuiper Belt objects that appear to have similar orbital parameters and similar surface compositions, suggesting they originated from the same parent body. The hypothesis is that Haumea suffered a major impact long ago that blasted material off its surface and distributed it across a region of the Kuiper Belt, creating what is now observed as the Haumea family of objects. If true, this would make Haumea the survivor of a catastrophic collision that is still traceable across a wide region of space through the scattered fragments it left behind. Quasar earns its own extended discussion because of what scientists discovered about it in 2023. something that genuinely reshuffled some assumptions in planetary science. Quasar was found in 2002 by Chad Trujillo and Michael Brown from images taken at the Palomar Observatory. At about 1,110 kilometers in diameter, it has a moon called Waywatt, discovered in 2006. For years, Quasar was a well-characterized mid-sized Kuiper Belt object, scientifically interesting, but not remarkable by the belt's sometimes extraordinary standards. Then, in 2023, scientists using the European Space Agency's Cheops spacecraft and a network of ground-based observatories announced the discovery of a ring around Quasar. The ring itself was not the surprise, the location of the ring was. Classical ring theory, built on the Roche limit concept, developed by French mathematician Édouard Roche in the 19th century, predicts that rings around a planetary body form within a certain critical distance, the Roche limit, where tidal forces from the body are strong enough to prevent material from clumping together into larger moonlets. Beyond that distance, material should accumulate into moons rather than maintaining a ring structure. Quasar's ring sits at about twice the distance where the Roche limit would predict a ring, in a region where, by classical theory, it should not exist. This unexplained location suggests that either the Roche limit calculations do not fully apply in all circumstances, perhaps when the particles are unusually cold and rigid, as they would be in the Kuiper Belt, or that there is some additional physics governing ring stability around small bodies that has not yet been fully understood. Whatever the reason, Quasar's ring has joined the list of things the Kuiper Belt has revealed that force scientists to revise assumptions they thought were settled. Sedna demands its own moment of extended contemplation, because it is in many respects the most mysterious object in the outer solar system. Discovered in 2003, at a distance of about 90 astronomical units from the Sun, already well beyond the classical Kuiper Belt, Sedna has an orbital period of approximately 11,400 years and reaches a maximum distance of about 937 AUs at its farthest point. When Sedna reaches aphelion, sunlight takes roughly 5.5 days to reach it. The Sun, from Sedna's surface at maximum distance, would appear as a tiny, brilliant point of light, much brighter than any other star, but not bright enough to cast a shadow or provide any meaningful warmth. The problem with Sedna, from a dynamical standpoint, is that it cannot be there. No known body in the solar system should be able to place an object in Sedna's specific orbit. Neptune, the most distant known giant planet, is too far away from Sedna's perihelion and too small in mass relative to the distances involved to have scattered Sedna into its current path. The classical Kuiper Belt's gravitational mechanics do not produce orbits like Sedna's. When Brown, Trujillo, and Rabinowitz found it in 2003 and calculated its orbit, the professional community was quietly puzzled. Several hypotheses emerged. Perhaps a passing star in the early solar system scattered objects from the inner Oort cloud into Sedna-like orbits. Perhaps the birth cluster of stars in which the Sun formed contained enough nearby stars to have gravitationally stirred the outer solar system before dispersing. Or perhaps there is an undiscovered large planet in the distant outer solar system whose gravity is responsible. This last possibility became more formally developed in 2016, when Michael Brown and Konstantin Batygin published a paper in the Astronomical Journal, arguing that the orbital characteristics of a cluster of extreme trans-Neptunian objects, including Sedna, were statistically unlikely to occur by chance and could be explained by the gravitational influence of a yet undiscovered planet with a mass of roughly 5 to 10 times that of Earth, orbiting the Sun at distances between perhaps 400 and 800 astronomical units, on a highly elliptical and inclined path. They called this hypothetical object Planet 9, a deliberate echo of the 9th planet designation that Pluto had lost a decade earlier. Planet 9 has not been found. As of 2025, no direct observation has confirmed its existence. The orbital clustering that Brown and Batygin identified as evidence for its existence has also been questioned by other researchers who argue that the clustering may be a statistical artifact of observational bias. We tend to discover distant KBOs in the parts of the sky we observe most often, and we do not observe all parts of the sky equally, which can create apparent clustering that does not reflect an underlying physical cause. The debate continues, and it may be resolved, one way or another, by the coming flood of data from the Vera C. Rubin Observatory's Legacy Survey of Space and Time, which is expected to discover tens of thousands of new KBOs and provide the statistical sample needed to determine whether the clustering is real. Arrokoth, the contact binary visited by New Horizons on January 1, 2019, represents something fundamentally different from all these larger objects. At about 22 miles long, it is not a dwarf planet, not a world with any apparent complexity of geology or atmosphere. It is a small, primitive, ancient object that has sat essentially undisturbed at 44 AUs from the Sun since the solar system was young. Its contact binary shape, two lobes gently pressed together in a snowman configuration, is its defining scientific feature. The two lobes appear to have formed separately in the same small region of the early solar nebula, and then slowly, over the course of perhaps millions of years, drifted together as their orbits gradually converged, finally touching and fusing at a velocity so low that neither shattered. What Arrokoth tells scientists about planet formation is significant. Models of planetary growth that involve violent high-speed collisions between planetesimals struggle to explain the preservation of Arrokoth's delicate, lightly cratered surface and its near-symmetric double-lobed structure. A collision between two comparable objects at high velocity would produce a very different and probably more irregular result. The gentleness of Arrokoth's formation instead supports a quieter model of accretion, one in which the earliest building blocks of planets grew from within swarms of material that were already moving in similar directions at similar speeds, allowing gentle accumulation rather than violent collision. This has implications not just for the Kuiper Belt, but for understanding how planets form in other solar systems, where astronomers now know that planet formation is extremely common. Sitting beneath and around all of this, providing the broader context into which the Kuiper Belt fits, is the hypothetical Oort cloud, the vast and so far unobserved shell of icy bodies that is believed to surround the solar system at truly extraordinary distances. The Oort cloud extends from roughly 2,000 AU to perhaps 200,000 AU from the Sun, which is nearly halfway to the nearest star system. It has never been directly observed. No telescope has ever resolved an individual Oort cloud object, but its existence is inferred from the orbital properties of long-period comets, those with orbital periods measured in thousands to millions of years that arrive from all directions in the sky, with no apparent preference for the plane of the solar system. Jan Oort, the Dutch astronomer whose name the cloud carries, proposed its existence in 1950. He noted that the orbits of long-period comets are highly elliptical, with aphelia clustered at very large distances, and that they arrive from random directions on the sky rather than from specific regions, which would be expected if they came from a belt confined to the ecliptic plane like the Kuiper Belt. From this he inferred the existence of a roughly spherical reservoir of icy bodies surrounding the solar system at very large distances, occasionally disturbed by the gravitational influence of passing stars, giant molecular clouds, or the tidal force of the galactic disk itself, which sends some objects falling inward toward the Sun as long-period comets. The Kuiper Belt and the Oort cloud together define what planetary scientists call the outer solar system's cometary reservoir, the two great stockpiles of primordial material from which the solar system draws its ongoing supply of comets. The Kuiper Belt supplies short-period comets with orbital periods under 200 years. The Oort cloud supplies long-period comets, the ancient wanderers that arrive from the depths of the outer solar system with orbital periods stretching thousands to millions of years. Together, they represent the most distant known regions of solar system territory, and together, they are the ongoing source of the objects that occasionally light up the night sky and, over geological time, have struck every planet in the inner solar system, including our own. Among the things that give the Kuiper Belt its particular character as a dangerous place is something that operates at the intersection of physics, geology, and evolutionary biology. The Kuiper Belt is not just a source of abstract impact hazard, it is the source of specific comets that have had specific effects on specific moments in Earth's history, moments that shaped what life is today and which species exist and which do not. Consider the connection between cometary bombardment and the water in Earth's oceans. The Earth formed relatively dry, The rocky material from which it was built contained little water in its early phase. Yet Earth's oceans are here, enormous and deep and essential to all life. Where did the water come from? One important source is believed to be cometary delivery from the outer solar system. Comets, which are largely composed of water ice, methane, and other volatiles, would have delivered significant quantities of water to the early Earth during the Late Heavy Bombardment. Measurements of the deuterium to hydrogen ratio in cometary water, the proportion of heavy water to normal water, have been used to compare cometary water with Earth's ocean water, with mixed results. Some comets match Earth's water chemistry closely, others do not. The question of how much of Earth's water came from the Kuiper Belt versus other sources is still being actively researched. Consider also the delivery of organic molecules. Comets are rich in organic chemistry. Carbon-bearing molecules of considerable complexity have been detected in cometary Haumea and, spectacularly, on the surface of Comet 67P by the Rosetta mission's instruments. Some of the organic molecules found in comets include simple amino acids and the chemical precursors to more complex biological molecules. This has led to the hypothesis, taken seriously if not yet confirmed, that cometary delivery of organic material may have contributed to the prebiotic chemistry that eventually, on Earth, gave rise to life. The Kuiper Belt, as the primary source of short-period comets, is in this view not only a potential destroyer of life, but a potential contributor to its origin, a dual role that captures something of the character of the solar system's history. Now let us think about the future, both the scientific future of Kuiper Belt exploration and the long-term future of this region's relationship with the inner solar system. New Horizons continues traveling outward through and beyond the classical Kuiper Belt as of the mid-2020s. The spacecraft's power source, a radioisotope thermoelectric generator that converts the heat from the radioactive decay of plutonium-238 into electricity, diminishes in output by roughly 3.5 watts per year. The total power available to the spacecraft decreases continuously, and mission controllers have had to progressively shut down non-essential instruments and systems to keep the most critical ones running. The spacecraft is expected to maintain contact with Earth, its signal received by the antennas of NASA's Deep Space Network, until sometime in the early to mid-2030s. In its final active years, the New Horizons team has been searching for a third flyby target along the spacecraft's precise trajectory, which cuts through a specific narrow corridor of the Kuiper Belt. Finding a target requires discovering a KBO along exactly the right path, at exactly the right distance, at a time when New Horizons still has enough power and communication capability to conduct a useful encounter. The James Webb Space Telescope has been used in this search, taking advantage of its extraordinary sensitivity to probe the faint, distant objects in New Horizons' path. Whether a third target will be found and reached before the mission ends remains uncertain, but the possibility exists. The James Webb Space Telescope has already begun making its own direct contributions to Kuiper Belt science, independent of any New Horizons-related work. Webb's instruments, sensitive in the near-infrared and mid-infrared wavelengths, where Kuiper Belt objects have distinctive spectral features, have begun characterizing the surface compositions of KBOs with unprecedented detail, detecting water ice, methane ice, carbon dioxide, and complex organic compounds on the surfaces of objects that are far too faint and distant for ground-based spectroscopy to analyze in such detail. These measurements are building up a more complete picture of the chemical inventory of the outer solar system, what materials are present in what combinations, how they vary across the belt's different populations, and what they tell us about the conditions under which these objects formed. The Vera C. Rubin Observatory, located on Cerro Pachon in the Atacama Desert of Chile, represents the next leap in discovery capability. The observatory carries the LSET camera, the world's largest digital camera at roughly 3.2 gigapixels, attached to an 8.4-meter mirror, and its operating plan involves repeatedly imaging the entire accessible southern sky every few nights, building up a time series catalog of billions of objects. For Kuiper Belt science, this represents a transformational capability. Where the current catalog of known KBOs numbers in the thousands, the LSST is expected to discover tens of thousands, perhaps hundreds of thousands of new KBOs, providing a statistical sample large enough to test formation and evolution models with real precision. If Planet 9 exists at anywhere near the predicted distance and mass, the LST will almost certainly find it during the 10-year survey. If it does not, the survey's result will argue strongly against its existence. There is also Japan's Destiny Plus mission, full name Demonstration and Experiment of Space Technology for Interplanetary Voyage Phaethon flyby and Deused Science, planned to visit the near-Earth asteroid Phaethon, which is believed to be related to the Geminid meteor stream and may have a Kuiper Belt origin. The mission, expected to launch in the late 2020s, represents part of a broader international program of small-body exploration that the Kuiper Belt connection has helped inspire. Beyond specific missions and specific instruments, the Kuiper Belt will continue doing what it has always done, slowly, persistently, over timescales that dwarf human civilization, perturbing objects from stable orbits and sending some fraction of them falling toward the inner solar system. This is not a threat that can be managed or mitigated on short timescales. It is a background condition of solar system life, a fundamental feature of the environment in which Earth exists. The probability of a civilization-threatening impact from a Kuiper Belt-derived object on any given human lifetime or generation is low. Over geological timescales, it is a near certainty that such events will occur again, as they have occurred before, repeatedly, throughout Earth's history. What has changed is our ability to detect and understand these objects in advance. The catalogue of known near-Earth objects, including comets from the Kuiper Belt that have been perturbed into inner solar system orbits, grows continuously as survey programs scan the sky with increasing sensitivity and coverage. Short-period comets, with orbits that cross or approach Earth's orbit, are tracked, their future trajectories calculated, their potential for Earth encounter assessed. The warning time for a cometary impact is generally shorter than for an asteroid, because comets can arrive from unexpected directions with less orbital history to analyze, but the science of detecting and characterizing potential impactors is maturing rapidly. Somewhere out in the Kuiper Belt right now, in the cold dark at 30, 40, 50 AU from the Sun, there is an object that will eventually fall inward. Something will nudge it from its stable orbit. A close approach to Neptune, a gravitational perturbation from a larger KBO, the slow accumulation of small perturbations over millions of years. It will begin the long fall inward, passing the orbit of Uranus, then Saturn, then Jupiter. It may be scattered outward again by Jupiter's gravity, sent back to the outer solar system or out of the solar system entirely. Or it may continue inward, developing a coma as the Sun's warmth reaches its surface, acquiring a tail, brightening in the sky above whatever creatures are then inhabiting the inner solar system. And if it falls on a world that harbors life, well, that has happened before. The craters are still there. The extinction events are written in the fossil record. The story does not have a final chapter yet. The Kuiper Belt is, in the end, several things at once. It is a frozen archive of the solar system's birth. It is a reservoir from which the solar system draws its comets, both the beautiful transient visitors and the potentially catastrophic impactors. It is a region of extraordinary complexity and diversity, containing worlds with mountains and glaciers, and rings and moons and organic chemistry, and, in the case of Pluto, what looks very much like an active, evolving geology. It is the place where our understanding of what a planet is, and what the solar system is, was fundamentally changed when Mike Brown discovered enough large objects there to make the old definitions untenable. And it is still mostly unexplored. Of the hundreds of thousands of objects estimated to inhabit the classical Kuiper Belt, only a few thousand have been discovered. Of those, only a tiny handful have been studied in any detail from spacecraft. The vast majority remain unknown, unobserved, unnamed, uncharacterized, tumbling in the cold dark beyond Neptune, preserving in their ancient ice whatever story they were there to witness when the solar system was young. Clyde Tombaugh, who found the first clue to all of this in 1930, spent most of his career never knowing what he had actually uncovered. He discovered not just Pluto, but the most prominent member of an entire hidden region of the solar system, and he did not live to see it confirmed. He died in 1997, 5 years after 1992 QB1 was found, long before New Horizons revealed what Pluto actually looked like. But the mission that finally showed humanity its first close view of his discovery carries a portion of his ashes. Clyde Tombaugh traveled in a small container attached to the hull of New Horizons, past Pluto, and on through the Kuiper Belt. And right now, as you watch this, he is still out there, moving through the dark at 36,000 miles per hour, heading toward the heliopause that marks the boundary between the solar system and interstellar space, carrying with him the remains of the man whose discovery started all of this. Gerard Kuiper thought the objects of the belt that bears his name would have been expelled long ago. He was wrong. They are still there, hundreds of thousands of them, surviving from the birth of the solar system, slowly depleted but far from gone. Kenneth Edgeworth, whose work came first, and who should perhaps be recognized more often, never saw the confirmation of what he predicted. David Jewett and Jane Liu spent 5 years searching before they found the first one in 1992. Mike Brown reshaped the solar system map with discoveries that ultimately cost Pluto its planet status and gave science a more accurate and stranger picture of the outer solar system than anyone had before. Alan Stern got to see the world his spacecraft was built to visit, revealed as something breathtaking and surprising, and entirely its own. The Kuiper Belt is not just the most dangerous place in the solar system. It is one of the oldest places in the solar system, a survivor of every violent episode in the solar system's history, scarred by ancient bombardments and depleted by migration, but still there, still populated, still active, still quietly sending its contributions into the inner solar system, and still yielding its secrets to every instrument patient enough and sensitive enough to look. There is a spacecraft out there right now, a few tens of astronomical units beyond Neptune, powered by the heat of decaying plutonium, transmitting data at the speed of light back to dishes in the California desert and the Australian outback. By the time you finish watching this video, it will be a few thousand miles farther along than when you started, and beyond it, spreading in every direction through the cold dark, are hundreds of thousands of icy worlds, ancient and frozen and patient, waiting to be understood. That is the Kuiper Belt. Thank you for watching. What you have just witnessed, laid out across this hour, is the story of how an enormous, frozen, ancient ring of ice and rock at the edge of our solar system was discovered, mapped, explored, and gradually understood to be one of the most consequential places in the entire history of life on Earth. That story is still unfolding. New data from New Horizons is still being analyzed. New KBOs are being discovered every year. The Vera C. Rubin Observatory is preparing to transform our catalogue of the outer solar system with tens of thousands of new discoveries. The James Webb Space Telescope is beginning to read the chemical fingerprints of objects that were previously too faint to characterize. Planet 9 may be confirmed or ruled out within the decade. The Kuiper Belt is not a finished puzzle. It is an open field of investigation, rich with objects that have never been observed up close, populated by worlds whose surfaces and compositions and orbital histories have never been studied in detail. Every new KBO that is discovered and characterized adds a data point to a map that is still mostly blank. Every comet that falls into the inner solar system from the Kuiper Belt is a sample of that frozen archive, briefly available for study before it is consumed by the sun's heat and lost. What makes this scientifically thrilling is also what makes it existentially sobering. The Kuiper Belt does not care about the civilizations in the inner solar system. It does not have intentions. It operates on timescales that make human history look like a brief flicker, orbital periods measured in hundreds of Earth years, geological processes unfolding over hundreds of millions of years, impact events separated by tens of millions of years on average, but capable of arriving at any time. The next major cometary impact on Earth could be tomorrow, or could be 10 million years from now. The Kuiper Belt makes no distinction. What we can do is understand it better. We can build better surveys and discover more objects and refine the statistical picture of the impact hazard. We can study the orbital mechanics of KBOs in greater detail and improve our models of how objects are perturbed from the belt into inner solar system orbits. We can develop the detection capabilities needed to find incoming comets sooner, giving more time to consider what might be done about them. None of this eliminates the underlying reality. The Kuiper Belt is a permanent feature of the solar system, and it will continue sending material inward for as long as the solar system exists. But understanding the source of a hazard is the first step toward managing its consequences. And beyond the practical considerations, there is the simple, profound fact that the Kuiper Belt exists. That out beyond the orbits of all 8 planets, in a region of space that most humans never think about, and that was not even confirmed to exist until 1992, there are hundreds of thousands of worlds, most of them never seen, most of them never named, each one a frozen record of conditions that existed before the Sun had finished forming. Each one has been orbiting the Sun since before multicellular life first appeared on Earth. Each one is older than every mountain on Earth's surface, older than the oldest oceans, older than the first single-celled organisms that would eventually, through billions of years of evolution, give rise to every living thing, including us. We sent a piano-sized spacecraft out to meet some of them, and it showed us mountains and heart-shaped plains and reddish organic compounds, and a quiet snowman of a contact binary, gently joined by 2 lobes in the dark, 44 AU from the Sun. And somewhere out there, in the cold and the silence, Clyde Tombaugh is still traveling. That is something. Think about the early days of Kuiper Belt science for a moment, because the contrast with where things stand now is remarkable. In 1991, the year before Dewitt and Liu confirmed 1992 QB1, the outer solar system beyond Pluto was, for all practical purposes, unknown territory. Astronomers had theoretical reasons to believe something was out there, and they had Pluto, sitting alone in the dark. The Kuiper Belt, as a confirmed observational reality, did not exist yet. The idea that there were hundreds of thousands of objects out there, dwarf planets with moons, objects with ring systems, contact binaries, scattered disk objects stretching to nearly 1,000 AUs, would have seemed wildly speculative, the kind of thing you might put in a science fiction novel, but not publish in a peer-reviewed journal without having the evidence to back it up. 30 years later, we have flown a spacecraft through the region. We have seen Pluto's mountains. We have discovered that one of the dwarf planets spins so fast it is no longer spherical. We have found ring systems around 2 Kuiper Belt objects, in locations where ring theory says they should not be. We have discovered an object orbiting the Sun on 11,400-year path, whose orbital characteristics cannot be explained by any known solar system body. We have visited a contact binary that formed by the gentlest possible merger of 2 primordial lobes of material, and that merger preserved evidence of the very first phase of planet formation in its undisturbed, ancient structure. The pace of discovery has been extraordinary, and it is about to accelerate again. When the Vera C. Rubin Observatory begins its full survey operations, the flood of new KBO discoveries will transform the field. Every discovery adds constraints to the models. Every new object with a well-measured orbit is another data point in the statistical distribution of KBO inclinations and eccentricities and semi-major axes. And from those distributions, scientists extract information about the history of the solar system, about Neptune's migration, about the Late Heavy Bombardment, about the structure of the primordial solar nebula, about the processes of planet formation that played out over millions of years in the distant past. There are also questions about the Kuiper Belt that connect to some of the deepest issues in planetary science and astrobiology. The question of water delivery to the inner solar system from cometary sources, how much of Earth's water came from the Kuiper Belt, what the isotopic signatures tell us about that delivery history, is directly relevant to understanding why Earth is wet and potentially habitable, while Mars and Venus are not. If water delivery from the outer solar system played a key role in making Earth habitable, then the architecture of the outer solar system, the position of Neptune, and the structure of the Kuiper Belt becomes a relevant variable in assessing the habitability of other planetary systems. The question of organic molecule delivery from comets is similarly important. If comets contributed meaningful quantities of organic precursors to the early Earth, then the chemical building blocks of life may have arrived partly from the outer solar system, assembled from the same frozen ices that now sit in the Kuiper Belt. This would mean that the origin of life on Earth is connected, in a deep and literal way, to the frozen archive of the outer solar system. The Kuiper Belt would not just be the most dangerous place in the solar system, it would be one of the places that made life here possible. These connections between the distant, frozen outer solar system and the warm, wet, biology-rich inner solar system are not coincidental. The solar system is a connected system, and processes in one region affect other regions. The migration of the giant planets, which redistributed so much material from the outer solar system into the inner solar system during the Late Heavy Bombardment, connected the Kuiper Belt to the inner planets in a fundamental way. The comets that still fall inward from the Kuiper Belt today are the continuing expression of that connection. The chemistry of those comets, and what it might tell us about the origin of life, is one of the most exciting frontiers in planetary science. What does all of this look like from the surface of one of these worlds, if we were somehow to stand on it? From Pluto's surface, the Sun would appear as an intensely bright star, roughly 1,000 times fainter than it appears from Earth, but still by far the brightest object in the sky. It would provide negligible warmth. The surface temperature is around -230 degrees Celsius, but it would be clearly visible and clearly directional. The sky would be almost entirely dark, filled with stars undimmed by any atmosphere dense enough to scatter their light. Charon would hang motionless in the sky, if you were on the hemisphere that faces it, a large disk 4 times the apparent diameter of the full moon as seen from Earth, never rising and never setting, a permanent companion. From an object in the classical Kuiper Belt, farther from Pluto, the scene would be even more extreme. The Sun would be dimmer, perhaps barely distinguishable from the brightest stars to casual observation, though still detectable as a light source by its steady position. The surrounding space would be populated with other KBOs at distances of millions of miles, far too distant to see with any reasonable optical system, but present in the gravitational environment, their masses contributing to the slow perturbations that, over millions of years, determine whether an object stays in its stable orbit or eventually falls inward. From Sedna, at its maximum distance from the Sun, approaching 937 AU, the Sun would be a brilliant but tiny pinpoint, indistinguishable by human eyes from a very bright star. The journey of light from the Sun would take 5 days to arrive. The gravitational pull of the Sun would be minimal, enough to maintain Sedna in its orbit over thousands of years, but not enough to feel as anything other than a very gentle acceleration. The isolation would be profound. None of these are places where life as we know it could exist. They are too cold, too remote from energy sources, too chemically simple at the surface. But they are places where chemistry is happening, where organic molecules are forming under the influence of cosmic radiation, where water ice sits in enormous quantities waiting for the right conditions to melt and become the liquid medium in which chemistry can accelerate. The Kuiper Belt is full of water. It is full of carbon compounds. The 2 key requirements for the kind of chemistry that produces life are present, frozen, and waiting, across hundreds of thousands of objects in the outer solar system. Whether any of that chemistry can express itself as life without a significant energy source in the neighborhood remains uncertain. The dwarf planets of the Kuiper Belt may have enough residual radiogenic heat in their interiors to have once maintained, or to currently maintain, liquid water beneath their icy surfaces. Pluto shows signs of geological activity today. If Pluto is geologically active now, at 39.5 AGUs from the Sun, the question of what energy source is driving that activity and whether similar activity occurs inside other, larger KBOs is scientifically interesting. Not because we expect to find life in the Kuiper Belt, but because understanding the energy budget and internal dynamics of these worlds adds to the inventory of conditions under which water can remain liquid and chemistry can proceed, and that inventory informs the broader search for habitable environments in the solar system and beyond. These are not idle speculations. They are the kind of questions that drive billion-dollar missions and careers, and the slow accumulation of knowledge across generations of scientists. The Kuiper Belt turned out to be a much more interesting place than Kuiper himself imagined, and every decade of study has added new layers to that interest. Let us come back to the direct danger one more time, because it is worth sitting with the specific scale of what Kuiper Belt-derived objects can do. The Shoemaker-Levy 9 impacts on Jupiter in 1994 released the equivalent of millions of nuclear weapons across 6 days. Those were fragments of a comet, and some of those fragments were perhaps 2 kilometers in diameter. The Chicxulub impactor that wiped out the non-avian dinosaurs 66 million years ago is estimated to have been roughly 10 to 15 kilometers in diameter. The energy released in that impact was on the order of 1 billion megatons of TNT. It vaporized an enormous volume of rock and sent it into the atmosphere. It set forests on fire across a continent. It injected enough material into the upper atmosphere to block sunlight across the entire planet for months. It triggered a chain of environmental collapse that ended the reign of the dominant land animals on Earth and opened the evolutionary space into which mammals, the lineage that includes us, eventually expanded. A comet from the Kuiper Belt falling on Earth would not announce itself far in advance. Short-period comets are typically only identified when they have already entered the inner solar system and are brightening as they approach the Sun. Long-period comets from the Oort cloud can arrive from directions and orbital planes not covered by the surveys optimized for near-Earth asteroids. The warning time for a large incoming comet might be months to a year or two, rather than the decades of warning that might theoretically be available for a known asteroid on a collision course. This is one of the reasons that the planetary defense community, the loose international network of scientists, engineers, space agency personnel, and policy specialists who think about impact hazard and mitigation, specifically tracks comets as well as asteroids, and why the completion of comprehensive sky surveys, like the LSST at the Vera C. Rubin Observatory, is considered a priority, not just for scientific reasons, but for the practical goal of knowing what is out there, in advance, with enough time to consider responses. The Kuiper Belt will remain what it has been for 4.5 billion years. It will continue feeding objects into the inner solar system at the slow, stochastic rate that the gravitational architecture of the solar system permits. Most of what falls inward will be destroyed by the Sun or scattered outward by Jupiter without ever threatening any inhabited world. A small fraction will cross Earth's orbit. A very small fraction of those will be on collision trajectories, and over long enough timescales, some of them will hit. What is different now from any previous moment in the history of this planet is that there is an intelligence here capable of understanding the system, tracking its objects, modeling its dynamics, and potentially doing something about what is on the way. That is not a small thing. For 66 million years since the Chicxulub impactor, the living world on this planet has had no say in whether it gets hit by what comes in from the outer solar system. For the first time in the history of the solar system, at least as far as we know, a species on one of the inner planets has developed the capacity to detect incoming objects in advance and to think seriously about changing their trajectories. That capacity is nascent. The tools are early generation. The deflection techniques are untested at scale, though NASA's DART mission in 2022 provided the first experimental demonstration that a kinetic impactor could meaningfully change the orbit of a small asteroid, a proof of concept for the principle, if not for the full-scale application. The gap between proof of concept and actual planetary defense capability for a large incoming comet remains enormous, but the trajectory is clear. We are beginning to take the outer solar system seriously as an environment that affects us, rather than as a distant backdrop. The Kuiper Belt has been out there the entire time, from the first hominids who looked up at the night sky and saw comets blazing across it, terrifying and inexplicable, portents of disaster in virtually every ancient culture, to the moment in 1992 when David Jewett and Jane Liu confirmed that the region beyond Neptune was populated with icy bodies, to the moment in July 2015 when New Horizons flew past Pluto and sent back images of mountains and glaciers and a heart-shaped ice plain. The Kuiper Belt has been shaping our solar system and our planet and the history of life on Earth. Now we know it is there. We can see into it. We can send machines to visit its residents. We can begin to read the record it contains. What we find there, over the coming decades of observations and missions and modeling, will teach us more about where we came from, how the solar system formed, what made life here possible, and what the universe is like beyond the boundaries of our immediate neighborhood. The Kuiper Belt is not just the most dangerous place in the solar system. It is one of the most important places in the solar system for understanding what the solar system actually is, and it is still mostly unknown. That, in the end, may be the most remarkable thing about it. Let us revisit the specific objects that populate the Kuiper Belt in greater depth, because these worlds deserve more than a brief introduction. They are the evidence from which everything else follows, the physical proof that the theories of solar system formation and dynamical evolution are correct, or where they are not, the anomalies that point toward what is still missing from our models. Take the Plutinos as a class. Pluto is the most famous member, but hundreds of other KBOs share its dynamical characteristic. They are in a 2-3 orbital resonance with Neptune, meaning for every 3 orbits Neptune completes around the Sun, a Plutino completes exactly 2. This resonance is not coincidental. It is the fingerprint of Neptune's ancient migration. As Neptune moved outward through the early solar system, it swept objects into this resonance, the way a broom sweeps debris into a pile. Objects that happened to be at the right distance when Neptune's orbit was passing through got captured into the resonance and carried outward with it, locked into this exact 2-3 ratio of orbital periods. The Plutinos are literally objects that Neptune picked up and carried during its migration, and the resonance is preserved billions of years later as direct evidence of that ancient process. Other resonances are populated too. The 1-2 resonance, where objects complete 1 orbit for every 2 Neptune orbits, contains a class called Twertinos. The 2-5, 3-4, and 3-5 resonances all have their own populations, each one a snapshot of where Neptune was at specific moments during its migration. Mapping these resonant populations is one of the ways planetary scientists reconstruct the history of Neptune's movement, essentially reading the geological record of the solar system in the orbital statistics of the Kuiper Belt. The cold classical Kuiper Belt, the population of KBOs between about 42 and 48 AUs with nearly circular, low-inclination orbits, is believed to be the most pristine surviving sample of the original solar nebula material. These objects, never significantly disturbed by Neptune's migration, have orbital characteristics that largely reflect the conditions under which they formed. They tend to have reddish surfaces, suggesting high concentrations of organic material, and many of them are binary objects, 2 KBOs orbiting each other at a much higher rate than expected from random encounters. The high binary fraction in the cold classical belt is one of the strongest pieces of evidence for the pebble accretion model, or streaming instability model of formation, because these mechanisms naturally produce bound pairs of objects that migrate together and end up orbiting each other, while high-velocity collision models would destroy such pairs. The hot classical belt, with its more elliptical and more inclined orbits, contains objects whose original orbital properties were stirred up by Neptune's migration and gravitational interactions with the giant planets. These objects have been through more dynamical history, their orbits perturbed repeatedly over billions of years. They tend to have different surface colors than the cold classical population, suggesting different compositions or different degrees of processing by radiation. The separation between the cold and hot classical populations is one of the more interesting structural features of the Kuiper Belt, and explaining it is one of the tests that formation models must pass. The scattered disk, the region beyond the classical Kuiper Belt extending to large distances, is populated with objects that had close encounters with Neptune during its migration and were scattered outward to high eccentricity orbits. Scattered disk objects typically have large orbital eccentricities, bringing them close to Neptune at perihelion before swinging out to much greater distances. Eris, with its perihelion of about 38 AUUs and aphelion of about 98 AUUs, is the most famous scattered disk object. These bodies are thought to be the direct source of the Centaurs, which are in turn the source of Jupiter family comets, making the scattered disk the primary pipeline through which Kuiper Belt material eventually reaches the inner solar system. The extended scattered disk, or detached objects, are KBOs with perihelia so far from the Sun that even Neptune's gravity cannot have directly placed them in their current orbits. Sedna is the best-known example. These objects are the most mysterious in terms of their dynamical origin, and they are the primary motivation for hypotheses like Planet 9. Their orbits imply some gravitational influence that the known planets cannot provide, and finding the source of that influence, whether it is a distant, undiscovered planet, the gravitational effects of passing stars in the Sun's birth cluster, or some other mechanism, is one of the most active areas of outer solar system research. The Kuiper Cliff is another unexplained feature of the belt. At roughly 50 AU, the number of KBOs drops off sharply, far more sharply than models of the Kuiper Belt's formation and evolution predict. If the belt simply thinned out gradually with distance, the population would decline smoothly, but observations show a cliff, a sudden, dramatic reduction in the density of objects at around 50 AU. This has been interpreted as evidence of some past event or ongoing process that cleared the region beyond 50 AU, possibly the gravity of an undiscovered planet that swept objects from that region. possibly the tidal influence of passing stars in the Sun's early stellar cluster, or possibly some aspect of the solar system's formation that concentrated material inside 50 AU and left the outer regions sparse. The cliff remains unexplained, and it is one of the standing puzzles of Kuiper Belt science. What all of these structural features share is their origin in the early history of the solar system. The resonant populations, the cold and hot classical belt populations, the scattered disk, the extended scattered disk, the cliff, all of these were established by processes that occurred in the first few 100 million years of solar system history, and they have been largely preserved since then, modified by slow, ongoing processes, but fundamentally set by those ancient dynamics. Reading the Kuiper Belt's structure is reading the history of the early solar system, a history that cannot be reconstructed from the inner planets alone, because the inner planets have been too thoroughly reshaped by their own geological and atmospheric processes. This is one of the most important reasons to study the Kuiper Belt. The inner solar system has been active enough, plate tectonics on Earth, volcanism and resurfacing on multiple worlds, atmospheric erosion, impact gardening, that the original record of solar system formation is largely erased. The asteroid belt provides some information, but it too has been significantly depleted and stirred up over time. The Kuiper Belt, in the cold dark beyond Neptune, is the best preserved record we have access to of the conditions that existed when the solar system was young. When we want to understand where the solar system came from, and by extension, where we came from, we look outward. We look to the Kuiper Belt. We send spacecraft out there. We build larger telescopes to see its residents more clearly. We spend years analyzing the data that comes back. This is what humans have been doing since 1992, when the first Kuiper Belt object beyond Pluto was confirmed, and the true outer solar system began to come into focus. It is what we will be doing for decades to come, as new instruments, new missions, and new analytical techniques expand our ability to read the frozen record of our origins that is preserved out there in the cold and the dark. The Kuiper Belt will not stop being what it is. It will not empty itself of objects on human timescales, or even on the timescales of geological eras. It will continue providing comets to the inner solar system, continuing a cycle that has operated since before Earth had any oceans. It will continue preserving within its icy bodies the chemical record of the solar system's birth. And it will continue offering surprises to anyone patient enough to look carefully. Ring systems in unexpected places, contact binaries that document ancient gentle mergers, dwarf planets with glaciers and mountains and thin blue hazes of atmosphere. The most dangerous place in the solar system is also one of the most ancient, one of the most scientifically valuable, and one of the strangest. Those things coexist in the Kuiper Belt without contradiction. Danger and beauty and scientific importance are not separate categories. They are all facets of the same cold, vast, ancient, inexhaustible place at the edge of the solar system we call home. There is a spacecraft out there right now. It has been traveling for nearly 2 decades. It passed Jupiter, then Saturn's orbit, then Uranus's orbit, then Neptune's orbit, then Pluto, then Arrokoth. It is now beyond the classical Kuiper Belt's outer edge, moving through the scattered disk and the outer solar system's unknowns, toward the heliopause, and eventually interstellar space. Its power is fading. Its instruments are being selectively powered down to extend the life of those still operating. Someday in the next decade or so, it will fall silent, its signal too weak to reach the antennas on Earth, its transmitter no longer powered. But by then, it will have given us everything it has. Every image of Pluto's heart-shaped plain and nitrogen glaciers. Every spectrum of Arrokoth's reddish surface. Every particle count from the outer solar system's unexpected density of material. All of it returned across billions of miles at the speed of light, received by dishes in California and Australia, processed by computers, distributed to scientists, published in journals, added to the slowly growing map of what the outer solar system actually is. The Kuiper Belt exists. It is real. It is out there. It has shaped our world and will continue to do so for billions of years to come. And we are, for the first time in the history of life on this planet, beginning to genuinely understand it. That, in all of its complexity and danger and wonder, is the Kuiper Belt explained. Now let us look at the history of how we have thought about the outer solar system over time. because that history is in many ways a story about the relationship between theory and observation, about predictions made before the tools to test them existed, and about what it takes to confirm something that is genuinely hard to see. Before 1992, the outer solar system beyond Neptune was more hypothesis than observation. The theoretical case for a belt of primordial objects in the outer solar system had been building since at least the 1940s, but the actual evidence, the direct detection of objects beyond Pluto, was absent. Astronomers who made theoretical arguments for the existence of a Kuiper Belt were essentially working on faith that the instruments capable of finding such objects would eventually be built and that the objects would turn out to be there. Science operates this way sometimes. The theory comes before the observation, and the observation either confirms or refutes what was predicted. In the case of the Kuiper Belt, the confirmation came, and it came substantially. Not only was the belt there, it was there in the way that theory predicted. A broad, flat disk of objects beyond Neptune, depleted compared to what must have originally existed, populated by bodies with orbital characteristics that told the story of Neptune's migration and the early solar system's dynamical history. The theoretical picture, built from arguments about solar system formation and the properties of comets and the need to explain certain orbital anomalies, turned out to be broadly correct in its essential features even before a single object was directly detected there. This is worth pausing on. Before 1992, nobody had confirmed the existence of a single Kuiper Belt object beyond Pluto. The region was as hypothetical as the Oort cloud remains today, and yet the theoretical framework turned out to be right in its broad strokes. The objects were there. The structure was roughly as predicted. The role of the belt as a source of short-period comets was confirmed. The dynamical evidence for Neptune's migration, preserved in the resonant populations and the orbital statistics of the belt, matched what the models predicted. What this tells us, beyond the specific facts about the Kuiper Belt, is something about how planetary science works as a discipline. It is not just observation and description, though those are essential. It is the development of physically motivated models that make testable predictions, and then the testing of those predictions with observations, and the refinement of the models when predictions fail, and the accumulation of confidence when they succeed. The Kuiper Belt's discovery and the subsequent decades of its study represent one of the cleaner examples of this process working as it should. The same framework is now being applied to Planet 9. Brown and Batygin identified the orbital clustering of extreme trans-Neptunian objects, built a dynamical model that could explain it, and made a prediction. There is an unseen planet with roughly specified mass and orbital characteristics at roughly specified distance. That prediction is now being tested by every wide-field survey capable of reaching deep enough into the outer solar system. If the prediction is right, Planet 9 will be found. If it is wrong, the surveys will not find it, and the orbital clustering will need to be explained some other way. This is science working as it should. The history of Kuiper Belt science is full of predictions that turned out to be right, and predictions that turned out to be wrong. Kuiper himself was wrong in predicting that the objects in the outer solar system would have been expelled long ago. Early estimates of the Kuiper Belt's mass were wrong. The belt turned out to be far less massive than predicted, which required updating the models of solar system formation to account for the mass loss. Predictions about the sharpness of the classical belt's outer edge were approximately right, but the mechanism responsible is still unclear. The Kuiper cliff was not predicted by standard models and remains unexplained. The existence of ring systems around small Kuiper Belt objects was surprising, and the location of Quasar's ring outside the Roche limit was surprising enough to potentially require updating of ring formation theory. Science is a process of proposing explanations, testing them, and updating them when the evidence demands it. The Kuiper Belt is a place where that process is visibly underway, producing both confirmations of established theory and genuine anomalies that push scientists toward new and better models. There is also the human dimension of Kuiper Belt science that deserves acknowledgement, because these discoveries are made by specific people, in specific circumstances, often after years or decades of patient, unglamorous work. David Jewett spent 5 years searching before finding 1992 QB1. Jane Liu, his collaborator, was a graduate student who became a postdoctoral researcher and eventually a professor during those years of searching. Clyde Tombaugh spent months scanning photographic plates before finding Pluto. Michael Brown discovered multiple dwarf planets and then became most famous as the man who killed Pluto, a label he has embraced with apparent equanimity, because the discovery of Eris was more important than maintaining any particular object's planetary status. Alan Stern has spent decades as an advocate for Pluto and the Kuiper Belt, from his role as principal investigator for New Horizons through his ongoing disagreement with the IAU's classification system, a disagreement rooted not in sentiment but in his scientific view that the IAU definition is physically incoherent. These people, and the thousands of scientists who have contributed to Kuiper Belt research since 1992, have built up our current picture of the outer solar system through the cumulative effort of professional lives spent asking specific questions, designing specific experiments, analyzing specific datasets, and publishing specific results. The picture is not complete. It will not be complete for a very long time, but it is already far beyond what existed when Jewett and Liu started their search in the late 1980s, and every year it grows a little clearer. Consider what the next 30 years of Kuiper Belt science might look like. The Vera C. Rubin Observatory, with its massive sky survey, will discover tens of thousands of new KBOs and provide the statistical foundation for dramatically improved models of the belt's structure and population. The distribution of discovered objects in orbital parameter space will tell scientists more precisely how Neptune migrated, how much mass the early Kuiper Belt contained, and whether the Kuiper Cliff is a real sharp boundary or a gradual decline that has been misread as sharp due to discovery biases. The James Webb Space Telescope will continue characterizing the surface compositions of known KBOs in unprecedented detail, building up a chemical map of the outer solar system that will reveal patterns in the distribution of water ice, methane, carbon monoxide, complex organics, and other materials across the belt's different populations. These chemical signatures are sensitive to where in the primordial solar system each object formed and what thermal processing it has undergone, and mapping them will add another layer to the reconstruction of solar system history. New Horizons, before it falls silent, may encounter one more KBO if a suitable target can be identified along its trajectory. The spacecraft will also continue collecting data on the outer solar system environment, the density of particles, the structure of the magnetic field, the behavior of the solar wind at large distances, data that will contribute to understanding the transition from the solar system's interior to the interstellar medium. Future missions to the Kuiper Belt are being discussed and planned. A dedicated mission to orbit a dwarf planet, Pluto, Eris, or one of the others, would provide the kind of sustained, detailed observation that flyby missions cannot deliver. Such a mission would need to travel to the outer solar system and then decelerate enough to enter orbit, which requires either very long travel times or advanced propulsion technology, or both. No such mission has yet been approved and funded, but the scientific return would be extraordinary. Months or years of close observation of a dwarf planet and its moons, mapping their surfaces in detail, measuring their compositions and internal structures, observing their geological processes over timescales long enough to detect change. The next generation of giant ground-based telescopes, including the extremely large telescope currently under construction in Chile and the 30-meter telescope planned for Mauna Kea, will provide dramatically improved resolution and sensitivity for observing faint outer solar system objects, enabling better characterization of known KBOs and supporting the search for faint new ones. All of this is coming. The Kuiper Belt will be more thoroughly known in 2050 than it is today. Some of its current mysteries will be solved. The question of Planet 9 will likely be settled one way or another. The origins of specific comets will be traced back to specific regions of the belt with higher confidence. The chemical map of the outer solar system will be substantially filled in. The models of Kuiper Belt formation and evolution will be tested against a vastly larger observational dataset and revised where they fall short. And there will almost certainly be new surprises. Every time scientists have looked carefully at the Kuiper Belt with better instruments, something unexpected has turned up. Pluto's geological activity was not expected at the level New Horizons revealed. Haumea's ring was not expected. Quaoar's ring location was not expected. The density of small bodies that New Horizons is detecting in the outer solar system is higher than expected. The history of scientific exploration of the outer solar system is a history of finding that reality is stranger and more varied and more complex than any prior model fully anticipated. That pattern of surprise is not discouraging. It is the expected behavior of science, encountering a universe that is genuinely more complex than any current model. The surprises are the leading edge of new understanding, the places where the map disagrees with the territory and the territory wins. Every time the Kuiper Belt has contradicted an assumption, the outcome has been a better model, a more accurate picture of how the outer solar system actually works. The Kuiper Belt will keep offering those contradictions for as long as we look carefully enough to notice them. And we will keep looking, because the outer solar system is not just scientifically important in the abstract, it is relevant to our own history, and possibly to our own future. Somewhere out in the Kuiper Belt right now, an object that will eventually become a comet is orbiting the Sun on a stable path. At some point in the future, millions of years from now perhaps, or perhaps much sooner, a gravitational perturbation will alter that path and send the object drifting inward. It will pass Neptune's orbit. It will encounter Jupiter, which will either eject it from the solar system or redirect it into an inner solar system orbit. If it survives Jupiter, it will begin developing a coma as the Sun's increasing heat reaches its surface. Its tail will grow. Its brightness will increase. Whether anyone is around to see it depends on things we cannot predict. Whether it poses any danger depends on the specifics of its orbit. But the physics is certain. This will happen. It is not a question of whether the Kuiper Belt will send more objects toward Earth. It is a question of when, and of what those objects are, and of what we can do about them when they come. The good news, if you are looking for it, is that we are paying attention. We are cataloging the objects we can see, modeling the dynamics of the outer solar system, developing planetary defense capabilities, and building the next generation of surveys that will expand our catalog dramatically. The era in which the outer solar system was essentially unknown, in which a large incoming comet could arrive with no warning and no prior record of its existence, is coming to an end. Not immediately, and not completely, but the trajectory is clear. The Kuiper Belt is no longer unknown territory. It is explored territory, partially mapped, partially characterized, with large blank regions still to be filled in, but with a clear outline now visible. The object that once seemed empty and unremarkable at the edge of the solar system, nothing out there beyond Neptune but Pluto and the void, turns out to be one of the most dynamic and scientifically rich regions we know of, packed with ancient worlds preserving the record of the solar system's birth, feeding comets into the inner solar system on geological timescales, shaping the history of every planet including Earth, in ways that are only now becoming clear. The Kuiper Belt is the most dangerous place in our solar system. It is also one of the most ancient, one of the most beautiful, and one of the most important places we have yet found in the exploration of the solar system. These things are all true simultaneously, without contradiction. A spacecraft the size of a grand piano is out there right now. It has been traveling for nearly 20 years. Its nuclear power source is fading. Its instruments are being carefully conserved. One day, not too many years from now, the signal will stop, and the spacecraft will continue in silence, traveling outward at thousands of miles per hour, carrying with it the ashes of the man who discovered the most famous of the worlds it passed, moving through the scattered disk and toward the heliopause, and eventually into interstellar space, leaving the solar system forever. But the data it sent back, those images of mountains on Pluto, that heart-shaped ice plain named for Clyde Tombaugh, those close-up photographs of a contact binary snowman floating in the dark 44 astronomical units from the Sun, that data is here. It is in archives and papers and journals and classrooms, and in the minds of the scientists who have spent years analyzing it. It will still be here when New Horizons has long since fallen silent, still teaching, still surprising, still adding to the picture of the most dangerous and ancient and extraordinary place in our solar system, the Kuiper Belt. There is one more dimension of the Kuiper Belt that has not yet been fully explored in this telling, and it is perhaps the one most likely to be overlooked because it operates on timescales that strain human imagination. It is the question of what the Kuiper Belt will look like billions of years from now, and what it tells us about the ultimate fate of the solar system. The Sun is a middle-aged star. It has been burning for about 4.6 billion years, and it will continue burning in roughly its current form for another 5 billion years or so, before running out of hydrogen fuel in its core. When that happens, the Sun will expand into a red giant, swelling enormously, engulfing the inner planets and transforming the outer solar system in ways that are difficult to fully predict, but can be broadly outlined. The Sun's increasing luminosity over the coming billions of years will gradually push the frost line, the boundary beyond which water freezes, farther and farther outward. The Kuiper Belt, currently at temperatures far below the frost line, will eventually experience warming as the Sun brightens. Over very long timescales, billions of years from now, some of the volatile ices on Kuiper Belt objects will begin sublimating, even at Kuiper Belt distances, as the Sun's output increases. The thin atmospheres of objects like Pluto, which expand and contract with Pluto's orbital approach to and retreat from the Sun, will become thicker and more sustained. The chemistry of the outer solar system will change. Objects currently stable and quiescent at extreme cold will begin behaving more like the comets that currently only activate when they fall into the inner solar system. When the Sun eventually enters its red giant phase, roughly 5 billion years from now, it will expand to a size that may reach the current orbit of Earth or even Mars. The inner planets will be consumed or severely altered. The outer solar system will be heated dramatically. The Kuiper Belt, at 30 to 50 AU, will be transformed. From a frozen archive of the solar system's birth to a warmer, more chemically active region, though still far from the Sun, even in its expanded phase. The objects currently entombed in permafrost will melt, or at least partially melt. The complex organic chemistry frozen in them for billions of years will become available to react, to change, to potentially support new chemistry of a kind not yet imagined. After the red giant phase, when the Sun sheds its outer layers and contracts into a white dwarf, a dense, hot ember of a star, slowly cooling over billions of years, the Kuiper Belt will undergo yet another transformation. The mass lost from the Sun during the red giant phase will alter the gravitational dynamics of the outer solar system, potentially destabilizing some orbits and scattering objects that have been stable for billions of years. The resulting system, orbiting a white dwarf in the far future, might look very different from what exists today, but some remnant of the Kuiper Belt's population might survive even this, continuing to orbit the cooling stellar remnant long after the Sun as we know it is gone. This is not a prospect that requires any practical concern on human timescales. 5 billion years is a number essentially impossible to make feel real. For comparison, the entire history of complex animal life on Earth spans only about 600 million years. Human civilization as we understand it is perhaps 12,000 years old. 5 billion years is 400 times the age of complex animal life, and nearly the entire current age of the solar system. Whatever happens to the Kuiper Belt in the Sun's red giant phase is as remote from our current circumstances as the formation of the solar system itself. But it is worth noting because it places the current Kuiper Belt in its proper context. The belt as it exists now, frozen, ancient, dangerous in its slow way, preserving the record of the solar system's birth, is a specific phase in the solar system's life. It will not always be this way. The frozen archive will eventually be thawed. The chemistry that has been locked in ice for 4.5 billion years will eventually be freed. What happens then, over timescales we cannot meaningfully conceptualize from where we sit, is an open question. For now, for the next billions of years, the Kuiper Belt will continue as it is. Cold, vast, populated with hundreds of thousands of icy worlds, feeding comets into the inner solar system at the slow rate that gravitational dynamics permit, preserving the chemical record of the solar system's origin, offering surprises to every instrument we point at it, and reminding us, gently, steadily, over geological time, that the solar system is not a safe and static environment, but a dynamic and ancient and consequential place, where things move and change and collide and build and destroy and preserve, across timescales that make our entire existence feel both precious and brief. We are here, in the inner solar system, on a warm, rocky world with liquid water and a thick nitrogen-oxygen atmosphere, and billions of years of biological history. And the Kuiper Belt is out there, cold and frozen, and full of the stuff that solar systems are made of, some of it already on its way toward us, most of it content to continue its patient ancient orbit for billions of years more. That is the relationship between us and the most dangerous place in our solar system. Not a relationship of active hostility or imminent threat, but a long, slow geological relationship, punctuated occasionally by events of tremendous consequence, stretching back to before the first life on Earth, and forward to the eventual transformation of the Sun and all its possessions. We are a part of this solar system. The Kuiper Belt is a part of this solar system. We formed from the same original cloud of gas and dust, the same solar nebula that produced the Sun and Jupiter and Neptune and Pluto and Arrokoth and all the trillions of unnamed icy bodies in the cold outer dark. The material in the Kuiper Belt and the material in your body were once part of the same interstellar cloud, the same vast diffuse collection of atoms drifting between the stars before gravity pulled it inward and the Sun ignited and the solar system formed around it. We are, in some sense, made of the same stuff as the Kuiper Belt. The elements in your body, the carbon, the oxygen, the nitrogen, the hydrogen, were all present in the primordial solar nebula. And while most of the material in the Kuiper Belt is the light elements and volatile compounds that congregated in the outer solar system, while the heavier elements condensed in the inner solar system to make the rocky planets, the chemistry is related. The organic molecules forming in the Kuiper Belt's icy surfaces, under the influence of cosmic radiation, the tholins that color so many of these objects reddish-brown, are made of carbon and nitrogen and hydrogen, the same elements that make up the organic molecules of life on Earth. The solar system is not divided into a dangerous outer zone and a safe inner zone. It is a connected whole, and the connections run deep into geological time and deep into chemistry. The Kuiper Belt is not somewhere else, entirely foreign, entirely separate from the world we live in. It is part of the same system, subject to the same physics, made of variants of the same materials, shaped by the same sun, and connected to our world through the comets that flow inward from the outer dark and through the ancient history of bombardment that shaped what Earth is today. Understanding the Kuiper Belt is, in a meaningful sense, understanding ourselves and where we came from, not in a mystical way, but in a physical, chemical, historical way. The frozen ices of the Kuiper Belt contain some of the oldest material in the solar system, older than any rock on Earth, older than any mountain, older than any ocean. They are a direct link to the time and conditions from which everything in the solar system, including life on Earth, ultimately derives. Reading them is reading the first chapter of a story that is still being written, still in progress, still producing new developments, new discoveries, new understanding. The Kuiper Belt is not an ending, it is a beginning, or more precisely, it is a preserved record of the beginning, still sitting out there in the cold and the dark, patient, ancient, enormous, and still, 4.5 billion years into the solar system's history, not fully known. That is what makes it worth paying attention to. That is what makes it worth sending a spacecraft the size of a grand piano on a 9.5-year journey through the outer solar system to photograph one of its residents from 7,800 miles away, an encounter that lasted minutes, that the spacecraft survived by the careful analysis of mission planners who spent years thinking through every possible hazard and chose to fly through anyway. That is what makes it worth building the largest digital cameras ever constructed and placing them on mountains in the Chilean desert to survey the outer sky every few nights for a decade, cataloging every object that moves. That is what makes it worth the work of Clyde Tombaugh, who found its most famous member in 1930 by blinking between photographic plates for months, and of Kenneth Edgeworth, who predicted its existence in 1943 and never saw it confirmed, and of Gerard Kuiper, whose name it carries despite his prediction that it would be empty, and of David Jewett and Jane Liu, who spent 5 years searching before finding 1992 QB1 and confirming that the belt was real, and of Michael Brown, who found the dwarf planets that forced a redefinition of what a planet is, and of Alan Stern and the New Horizons team, who spent a decade designing, building, launching, navigating, and ultimately guiding a spacecraft past Pluto and beyond. These people, and the hundreds of other scientists whose names do not appear in popular articles about the Kuiper Belt, but who contributed essential pieces of the picture, did this work because the outer solar system is worth understanding, because the most dangerous place in the solar system is also one of the most important places, one of the most ancient places, one of the richest places for scientific inquiry we have yet found. And right now, out there, it continues. The belt turns. The comets drift inward. New horizons travels beyond it. The cold and the dark persist across hundreds of astronomical units of space, preserving within them the frozen record of the beginning of everything in our solar system. That is the Kuiper Belt. Dangerous, ancient, vast, extraordinary, and still mostly unknown. Thank you for watching. One final thought before we close. Because the Kuiper Belt offers something beyond science, something that is harder to quantify, but equally important. It offers a particular kind of perspective. We live in a moment of extraordinary capability and extraordinary anxiety. Human civilization is more technologically powerful than at any previous moment in history, and that power creates both opportunities and risks that previous generations could not have imagined. In the midst of all that, it can be genuinely clarifying to look outward at the Kuiper Belt and hold both truths simultaneously. That we are very small, in a solar system of enormous scale, in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies, and that we are also, as far as we know, the only species in this solar system that has figured out the Kuiper Belt is there, has sent a machine to photograph Pluto, has decoded the dynamical history of Neptune's migration from the orbital statistics of Kuiper Belt objects, has begun to understand the role of cometary bombardment in delivering water and organic molecules to the early Earth. Both of those things are true at the same time. The Kuiper Belt humbles us with its scale and antiquity, and it also represents something remarkable about what the species that evolved on this small rocky world in the inner solar system has managed to do with its brief existence. We looked outward. We built instruments. We sent machines. We decoded the history. We found the frozen record of the solar system's birth and began, carefully and slowly, to read it. That is worth something. Whatever else is true about this moment in history, that is worth something. The Kuiper Belt is out there. Now you know what it is.